I will start with the topic of simulation. The standard approach for dimensioning a torsional elastic steel spring coupling is a frequency-based steady-state torsional vibration analysis. The big advantage of a steady-state analysis is the relatively low computational power, and it's relatively easy to compare the results. But some specific application needs an additional transient simulation too, like complex system or special running conditions. The aim in this part of this presentation is to show the challenges of this kind of calculation and the new opportunities for transient analysis. This brings me to my next point, challenges of transient TV simulations. Standard examples where transient TV simulations are used are events with rapidly changing external excitations like a generator short circuit or an ice impact simulation. Another example are systems with running conditions that vary strongly over the considered time horizon, like the base working point at an engine run-up or the environmental conditions for wind turbines. All these have non-periodic results are not a sum of finitely many orders of vibrations. Based on the lost periodicity and the linearity of the external forces, it cannot be modeled anymore in a frequency domain model. Therefore, this application has to be simulated in the time domain calculation to ensure safeness in all possible conditions. The picture on the left side shows the typical periodic engine excitation. On the right side show a non-periodic excitation. In this case, it was from a short circuit excitation. Furthermore, there is an additional challenge for comparison with steady-state torsional vibration calculations. Because the splitting of dynamic components and static components in order-based solutions is not even possible in transient simulations. Based on the challenges, additional filtering techniques must be applied for approximating the mean speed in transient simulations. Additionally, system speed is necessary for this, and engine speed controller is needed in the system. With the help of a speed controller and an engine torque limiter, speed drops can be compensated on high excitations. On the left side, there we can see a result of a steady-state calculation. Here we can see the torque the occurring torque of a coupling. The right side shows the occurring torque of a coupling from a transient calculation. These two pictures show how different these results are. So the evaluation if the steel spring coupling can withstand the occurring torsional torques in the transient calculation is a challenge. The approximation of the static load is very important because the definition of the permissible elastic vibratory torque for continuous or transient operations are directly dependent on the static torque. In more detail how we solve this kind of problem, I will explain on the next slides. On the right side, you can see an example of the permissible elastic vibratory torques of a semi-reversible coupling, where the x-axis shows in the percent of mean torque, and the y-axis shows the permissible elastic vibratory torque per nominal torque in percent. As already mentioned, a main challenge are the frequency-depending parameters. Frequency-based models are typically created for different damping and stiffness definitions, and these have a big impact in the calculation results. The same challenge have the steel spring couplings in the time domain too, because the different frequency-depending properties must be adapted, like for undimensioned damping factors and dynamic stiffness. At the moment, there is no general approach how to transfer models from steady-state calculations to the transient simulations. For this reason, I present two possibilities to model a coupling in a transient simulation. This is also a possibility for other frequency-dependent parameters like an engine or a propeller. The first one is the elimination of the frequency dependency. For this, a clearly dominating frequency is searched, which is also a good approximation for a steady-state model. These frequencies are called dominant or major frequencies, in case if only a single order is present in the torsional response of the vibratory twist and velocity. This method can easily be applied to the stiffness and damping calculation. But the first method cannot always be applied because often the case that not only one order can be identified as a major order in the system. The second method is a weighted major order. So to avoid the first kind of problem, we made a weighted main order, and this is calculated based on the magnitudes in the total signal. This is used for the stiffness and damping calculations. This order is calculated by using a fast Fourier analysis over a specific time range of the simulated results. The picture on the left-hand side shows the total result twist over time. And on the right side, there we can see the corresponding Campbell diagram with the single filtered order. So from this weighted major order will be detected, and with this detected major order we will be calculated the frequency-dependent parameters of the coupling and updated these parameters during the simulation at the calculations. In this case, it will be calculated the stiffness parameters of the coupling. So in addition, the detection of major frequency to stiffness and damping should be split, because based on the equation of motion, the detected major order for the calculation of stiffness can be different than to the calculation for relative damping. So the operation for damping and stiffness is detection in the same, but the parameters for using are different. On the left side there you can see the dynamic velocity difference. So here the red line shows the calculated major frequency for relative damping. And on the right side you can see the dynamic twist. Here is the red line, the major frequency for a stiffness calculation. So these two pictures show that the major frequency for stiffness and relative damping is not always the same. As a next example for transient calculation, I will show you a power plant. The focus on this slide is on the time domain calculation. In this calculation, we check the short circuit event in different cases. This event occurs if the alternator has a short circuit. Then the resulting torque, called short circuit torque, is fed into the system like an engine excitation. As we can see, the occurred torque in the coupling, the occurring torque is well below the buffer limit, and so we can propose the coupling. On the right side, there we can see the occurring torque in the alternator. This is the short circuit torque that's fed into the system. The torque that will be fed into the system is 5 times higher as the occurring torque in the coupling. So this means it is more important how long and intense this excitation remains in the system and until it drops down again. This has the most influence. Here we can see the occurring torque in the coupling in more detail. Based on the static torque, the occurring torque in the coupling is shifted. This can be seen here because the oscillating torque is here roundabout oscillated about of 60 kilonewton meters. The FEM model on the right side shows how this effect looks inside the coupling. In this picture, the coupling is fully deflected. So the combination with static torque and vibratory torque based to the fact that the safety margin to the buffer limit on the forward side is lower than to the reverse side. So in this study was the focus on the noise reduction in a wind turbine. The basic idea of this study is to reduce the excitation on its source to avoid the formation of structure-borne sound, instead of trying to damp the transfer of noise at any location in the drivetrain structure. In wind turbines, one of the main sources of drivetrain are drivetrain and noise and excitation caused by the gear mesh in the second planetary stage. Distortional excitation includes the planetary carrier and resonance with the gearbox housing, because of the torsional vibration spread to the entire drivetrain. Due to the complexity of the problem and the many possibilities, we focus in this study on the kind of option of a noise attenuating solution in a three-step gearbox. This can be seen here, where we integrate the coupling. It is an elastic coupling that is integrated in the spur gear at the third stage. The integrated coupling in the spur gear is so smart because we don't need an additional space. Based on the linearization of the system, a frequency analysis is carried out. For this, a harmonic input signal, such a sine curve, is put into the system at both planet carriers to obtain the frequency response of this linearized system. In the study, the main problem with the noise was the planetary gearbox on the second stage, on the sun shaft, called here in the picture Sun 2. This figure presents the results of the frequency analysis. The blue graph represents the system behavior of the reference model, whereas the red graph shows the effect with the included coupling. The advantage of this coupling is based on the higher stiffness. The resonance is shifted out of the critical area and damped in addition. As my last big topic today, I will present you the new approaches for measurements in the next slides. I will give you some insights how we deal with these challenges. The picture on the right side shows the measuring principle of the steel spring coupling. It consists of two measured teeth rings, and of each teeth ring a sensor is mounted. Each sensor measures the vibratory angle. In between, we can calculate the twist of them. There are two kinds of monitoring options for elastic steel spring couplings. The first one that I want to explain is steady state monitoring. At this option, there we have for each order the measured signal over speed. Both rings get a reference tooth to measure the static twist of the coupling. As already mentioned, the static twist is very important because it's directly depending on the evaluate of the coupling. At this processing, the angular signal is filtered and eliminates all frequencies above and below the fixed orders to avoid non-stationary effects in the measurement results. Additionally, the FFT analysis only considers the dynamic signal that comes from the total angles. Secondly, I want to present the transient events. The pulses were directly evaluated by reconstructing the total angle signal over the entire measurement time range. In this kind of monitoring, is a reference tooth not necessary, because the measurement starts with the last engine stop, and so the static offset can be calibrated without any load on the coupling. Here is an example of a steady state measurement of a coupling. Here we can see in orange the synthesis that is over all single orders. Directly below we have the filtered single orders. The third one was in this system the major order. The small step that we can see here was from the turbocharger changing condition during the measurement. On the right side we can see the speed sweep. This was happened during the measurement. It is very important that the speed increasing during the measurement is very low to ensure a steady state measurement. Directly below we can see the power curve. The light blue points are the measured power curves, and the dark blue graph below are the calculated power curve that we are using for the evaluation of the measurement. This is for the transient monitoring an example. On the left side, the graph shows the measured speed sweep over the time, and on the right side, can see the corresponding twist from the coupling. At the beginning, the engine is accelerated to a certain speed by means of an electrical motor. The engine can only ignite from this point in time. This shows up very well in the speed sweep. Since the acceleration tends to be vibration-free at the beginning and the vibration comes from the point of ignition, which then transforms itself into a constant vibration. These points in time can also be easily followed in the coupling. At the beginning, when the electrical motor is still working, the coupling is in steady state. And after then, the resonance builds up. As already mentioned, the second method for monitoring needs a big amount of data, because these are long-term measurements. Long-term measurements have the challenge of structural processing and storing of the amount of data. As a solution for this problem, we use an optimized cloud-based data processing framework, as shown in this slide. We use three major levels for data processing: the data streaming, the database and querying, and the customer visualization. With this new data streaming option, it is now possible to continuously push TV measurement data online to perform a detailed multi-level analysis. For this, the measurement data are shared into the processable data packages. For which there are many post-processing routines connected to the streaming platform. Additionally, information can be connected to the evaluation algorithms. This information comes from the several databases that include information about design production and quality control. It is also a possibility to connect this with measurement results and TV calculations from the past. Finally, an online visualization tool is developed, with which the measurement analysis of the large datasets can be performed. In this presentation, the developments of simulation and measurements of torsional vibrations for torsional elastic couplings are analyzed. I present you two kinds of options. How can frequency-dependent parameters adapt in transient simulation models? And as a new development for TV monitoring for long-term processing for steady-state and transient operations, this is presented. Thank you for your kind attention.
Thank you very much, Ms. Windhofer.